In the last video, we had discussed carboxylic acids, and we used resonance to explain why they have such strong acidic properties. And we noticed in the previous video that these two oxygens, the carbonyl oxygen and the hydroxyl oxygen, they're both sp2 hybridized. And for the carbonyl oxygen, both of these unshared pair of electrons are sp2 electrons. For the hydroxyl oxygen, it has an unshared pair of sp2 electrons and an unshared pair of p orbital pi electrons. And at the end of the last video, after we explained the acidic properties of carboxylic acids and how these acidic properties are so much enhanced through resonance, we ended the video with this question: since we have all these unshared pairs of electrons, is it possible to attach a proton to one of them? In other words, can a carboxylic acid have the properties of a base? That seems counterintuitive, but in fact the carbonyl oxygen of a carboxylic acid is more basic than the carbonyl oxygen of an aldehyde or ketone. And let's see why. If we have, again, a carbonyl group and attached to the carbon is some other organic group, and just a simple hydrogen, then that's an aldehyde. If instead of a hydrogen we have another organic group attached to it, then that's a ketone. And there is no resonance structure available here unless some of these might have pi orbitals on them on their other atoms, but we're just going to consider a generic one where there isn't. So what happens here then is we have carbon attached to a very electronegative oxygen, and the oxygen has two pairs of electrons to pull towards it from the carbon, from the sigma bond and from the pi bond. So this oxygen carries a significant partial negative charge, leaving the carbon with a significant partial positive charge. So it's possible then to put a proton onto here. Now the oxygen no longer has a partial negative charge, and in fact with that proton attached to it, it's actually going to have a positive charge, and its electronegativity is greatly decreased, so the carbon here no longer has a partial positive charge. So we can put a proton on an aldehyde or a ketone, but there's no resulting resonance stabilization, either before or after. Now, here we have a generic carboxylic acid. What happens if we put a proton onto one of these sp2 electrons? Let's see. We have then the carbonyl oxygen, sp2 pair of electrons, and now a proton here. So this is going to have a positive charge. And notice now we're set up to have a resonance system, because here we have a pi bond. Here we have an unshared pair of pi electrons. And what can happen is, as we saw now in our previous videos, as we've been working along with this, we can imagine oxygen acquired taking both of the pi electrons. course, in the bond here, the pi bond, the carbon puts up a pi electron, and so does the oxygen, and they share them. But we imagine oxygen keeping both of those pi electrons. So we now have a single bond. And the oxygen no longer has a positive charge because it acquired an extra electron that it stole from the carbon. So carbon lost an electron, but here we have a lone pair of pi electrons. So again, we can imagine these swooping in to be shared between the carbon and the oxygen. In this double bond, but it leaves oxygen, this oxygen, with a positive charge because we have this pi bond, but oxygen is donating both electron pairs to form that pi bond. But this gives us then a valid resonance structure, and in fact, this and this are symmetrical. Imagine here we have carbon attached to this R group. If we just rotate this 180 degrees, then this would be down here, and this would be up here. So in fact, these two resonant forms are symmetrical with each other. And if you go back and look at the other videos, you'll see that we don't have any separation of positive and negative charges as we had in some of the other examples. So this is actually a pretty well stabilized resonance system. So that is why for a carboxylic acid, its carbonyl oxygen is actually more basic than what you'd find for a typical aldehyde or ketone because of this resonance stabilization. That's something you may not have thought of before. And in fact, there are specific organic reactions that depend upon, for carboxylic acid, to have the carbonyl oxygen acquiring a proton. Now, having said all that, what about this oxygen? That also has unshared pairs of electrons. These are sp2 electrons. These are unshared pair of pi electrons. Well, we're not going to put a proton here on these because that would mean then that they're no longer available to be delocalized in any kind of resonance system with this adjacent carbon atom that has that pi bond. So a proton will not attach to the pi electrons. But we could imagine putting it here. Then this has a positive charge. But remember now from our carbonyl group, the oxygen has a substantial partial negative charge, and that carbon there has a substantial partial positive charge. And we've got these two positive charges fairly close together if we put a proton on here. And that's not a very stable system. So the bottom line then is that if we take a generic carboxylic acid and put it in an acidic medium, the proton is not going to go here or here, it's going to go here. And again, as we saw, not only is that possible, but in fact it sets up a pretty decent resonance system, again explaining why for a carboxylic acid the carbonyl oxygen is actually more basic than what you find with most typical aldehydes and ketones. Okay, that's all I want to say for this video. A reminder that the playlist for the videos is featured at the website digital carboxylic-university.org. Oh, and in the next video what we're going to do is consider amides, where we have this type of molecule. Instead of a hydroxyl group, now we have a nitrogen here. What would be, how acidic are the amides compared to carboxylic acids? We'll discuss that in the next video.